All right, y'all. Sorry this is getting out so late. Just didn't want to test the technology too much more this week with all of our issues at the beginning of the week. So I'm going to be going over the self-assessment FRQs, the two from last week with rate and accumulation. So starting with our 2016, we have water being pumped into a tank at a rate modeled by W of T is equal to 2000 E to the negative T squared over 20 liters per hour from 0 to 8. Where T is measured in hours, water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing from 0 to 8. And then they give us some selected values of R of T up above. At time T equals 0, there are 50,000 liters of water in the tank. So that's our initial condition. W is representing water going in, and they give us a nice easy equation to work with. R is the rate of water going out, and they give us a not so easy, but still not too hard table of values to work with. Both W of T and R of T are rates, so they are that first derivative that they're representing. So let's talk about A. We want to estimate R prime of 2. So we want to estimate the rate of water being removed. So if I want to estimate, remember, anytime they ask us to estimate the derivative, what are we going to do? We want to do that AROC, that average rate of change. So for part A, R prime of 2 is equal to, we want to estimate 2, so we want to pick values on either side of 2, so 3 and 1. So R of 3 minus R of 1 over 3 minus 1. So R of 3 is 950, so 950 minus 1190 over 2. And that gives us did I do that wrong? 1190. Negative 120. So negative 120. And then it's the rate of the rate. So the rate of R of T. R of T is measured in liters per hour. So the rate, R prime of T, would be liters per hour squared. It's that acceleration value. Okay, so that's part A. Part B, we want to use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. And then as a second spot, is this an overestimate or underestimate of the total amount of water removed, and give a reason. Okay, so first off is a Riemann sum. Riemann sums are pretty straightforward. Okay, it is a left Riemann sum, which means I'm going to be using these subintervals. I'm going to be multiplying them by the leftmost value for each of the intervals. So 1 times 1340 plus, let's see, 2 times 1190 plus 3 times 950 plus 2 times 740. Remember, this is estimating the area under the curve, so this is estimating if this helps out. The integral from 0 to 8 of R of T. And use our squiggly equal signs to show that's just an estimation. Okay, so then type all that into our calculator. So 1 times 1340, that's just 1340. So 1340 plus 2 times 1190 plus 3 times 940, I believe. Yep. No, 950. Is it 950? It is 950. Plus 2 times 740. There's where that 40 was coming from. And that gives us 8,050. And now, once again, talking about units. So we did the integral of R of t. R of t is liters per hour. The derivative of R of t is liters per hour squared, which means the integral of R of t, we're going from velocity, our first derivative, to our original function. So it's just going to be an amount. So this should just be liters. Okay, now the second part of part B is they want us to talk about whether this is an overestimate of the value of liters removed or an underestimate of the value of liters removed. So remember, when we first talked about Riemann sums, talking about if it's an overestimate or underestimate, it depended on the shape of the function. So our function, our R of t, is decreasing over time. It's going down. So we have a function going like this. All right, this is R of t. So if I'm doing my little Riemann sum, my left-hand Riemann sum, as I draw those leftmost rectangles, you can probably see that my rectangles are going to be up above the curve because it's decreasing over time. So because it's a decreasing function, my left rectangles are going to be up above the curve. So that would be an underestimate. So it is an underestimate. And we would say because R of t is decreasing. On 0 is less than or equal to t is less than or equal to 8. So the whole time, curve is decreasing. All right. That takes us through part B. Part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so now we're talking about the whole tank. So we want to know how much water is in the tank at the beginning at time t equals 0, and how much water is in the tank at the end. So how much water is going into the tank and how much water is being taken out of the tank. So now we're going to include both R of t and W of t. So this is our big integral equation that we've kind of been talking about on all of these. So for part C, we have our initial condition. So our initial condition is 50,000 liters of water in the tank. So 50,000. Let's call this, I don't want to use T. We'll say V for volume of the tank. So V of t is equal to 50,000 plus, now we're going to do the integral of both of our equations because we want to find that amount of water. So plus 0 to 8 for our time. And then it is, which one is representing water pumping in? W of t is pumping in, so W of t minus, so I'm not going to minus R of t because R of t isn't actually a function. R of t is a table of values. But we did already find the amount of water removed, or our estimate. They even tell us in part C, use your answer from part B. So instead, I'm just going to minus 8,050. And I'm not integrating 8,050 because that's already an amount in liters. So 50,000 is an amount in liters. 8,050 is an amount of liters. The only thing that's not an amount in liters is W of t because that's liters per hour. So I need to integrate W of t to get the amount of liters that comes into the tank. And that's going to be my answer. So go in here. I hit math, then option 9. So math 9, we're going from 0 to 8. Before that, I can add in my 50,000. So 50,000 less the integral from 0 to 8 of W of t, which is this big old mess, 2,000 e to the negative t squared over 20. So 2,000 second e to, is it negative t squared? Yep, negative t squared. 20 dt. And then I want to add 8,050, that estimate we found in part B. We get 65,886. Just checking, making sure I didn't lead you astray. What did I do wrong? Oh, I added my 8,050. My bad. We're subtracting the 8,050. Like, duh. There we go. 49,786.195. We always want to round to that 3 decimal places, unless it tells us to do it to a whole number. Let's see. Nope. So 49,786. .195, and then liters, because that is an amount in liters because we integrated. All right, now the last part for part D. Is there a time t where the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? And explain why or why not. Okay, so we want to know, is there a time where the rates are the same? So really what I want to know is there a time where what we really want to prove is that W of t and R of t are equal to the same value. Now, it's a little hard to consider, find what that value is going to be equal and then compare, because, there's literally any value that they're equal to. But if W of t and R of t are equal to each other, then W of t minus R of t should equal what? They should equal 0 because they're the exact same value. So we can kind of account for all those values if we consider W of t minus R of t. Now, how can I prove that at some point W of t minus R of t is equal to 0? Well, to prove that, I just need to use my intermediate value theorem. Intermediate value theorem is how I prove that a value exists on some interval. And the interval I'm trying to prove that it exists on is between 0 and 8. So to prove that W of t minus R of t equals 0 at some time between 0 and 8, I have to know what's happening on the endpoint. So I have to know what's happening at W of t minus R of t at 0 and at W of t minus R of t at 8. So let's first find W of t, or W of 0 minus R of 0. So W of 0 minus R of 0. W of 0, if I plugged 0 into this equation here, that would be e to the 0, which is just 1. 1 times 2,000 is 2,000. So that would be 2,000 minus 1340 for R of t. I'm getting that from the table, which is equal to 660. Okay. And I'm not really worried about units at this moment in time because my answer is not really going to be my units. Then the other one I want to find is W of 8 minus R of 8. All right, and this one I'm going to have to plug in because I don't know what that to the 8 is. So 2,000 e to the negative 8 squared, I believe. Yep, negative 8 squared divided by 20. Divided by 20, not minus 20. And just to make sure everything's accounted for correctly, let's make sure we put that 8 in some parentheses. And we'll be a little extra cautious and add some parentheses here. All right, so we get 81.524. And then I am subtracting 700, which I don't really need to know exactly what that is, but it's about negative 620. We can be rough because it doesn't have to be perfect. All right, so at W of 0 minus R of 0, I got positive 660. At W of 8 minus R of 8, I got negative 620. So I'm going from positive to negative. So from 0 to 8, I have to go from a positive value down to a negative value. At some point, does W of t minus R of t have to equal 0? Yes, that's what IVT says. So as a conclusion, we want to make sure we talk about all the things for IVT. So first of all, function has to be continuous. Up here, differentiable, which implies continuity. The They don't tell us about W of t, but it's a function involving E. E is continuous for all x values. It just goes nice big swoop. So they don't really need to tell us that. We should be good. So we'll say that W of t minus R of t is continuous on 0 to 8. Close interval. So 0 to 8. And W of 0 minus R of 0 is greater than 0. And W of 8 minus R of 8 is less than 0. So we have function is continuous. At 0, we're positive. At 8, we're negative. Therefore, W of t minus R of t equals 0 at some t on 0 to 8. Open interval. Hey, and that's basically just quoting IVT to a t. Nice short little sum up sentence. Okay, so to kind of recap what we did for everything for our first question, for part A, we needed to estimate R prime of 2. Since we are estimating the derivative, we applied our average rate of change, our f of b minus f of a over b minus a. We chose 3 and 1 because 2 is in between 3 and 1. For part B, we wanted to use a left Riemann sum using the subintervals indicated by the table. So we made the 4 subintervals indicated in the table, and we multiplied by the left value for a left Riemann sum. Then once we found that, they asked us to determine if it's an over or underestimate. We determined it's an underestimate because our function R of t is decreasing in values. It goes from 1340 down to 700. So it's decreasing the whole time, which means our left little rectangles are going to be above, which means it's, oh, why did I write underestimate? I'm crazy. Overestimate. Sorry. Sometimes. Overestimate. Sometimes I'm crazy. Ignore what I said earlier. It's an overestimate because R of t is decreasing. As you can clearly see that the rectangles are up above the curve. Ignore what I said earlier. All right. For part C, V of t is equal to 50,000. We are trying to estimate the total amount of water in the tank. So we accounted for the original amount of water in the tank, which was 50,000 at time 0. We added the integral of the rate of water entering, which was going to give us the amount of water that goes into the tank over those 8 hours. And then we took away our estimate for the amount of water that is being pumped out. Because we want to take away all the water that's leaving. So 50,000 liters, the integral of this is going to be some amount of liters, and then minus 8,050 liters gave us 49,786 liters after 8 hours. So that's our big kind of mega equation. Then last but not least, for part D, they wanted us to find a time when the rate water is going in is equal to the rate water going out. So the only way we could really account for all those possibilities is by finding when W of t minus R of t is equal to 0. Because if W of t minus R of t is equal to 0, then that means the rate of water going in and the rate of water going out is the same number. So then to prove that that was equal to 0, we used IVT because IVT proves that values on the original function are in between two values. So we plugged in at our endpoints. And since we had a sign change of going from positive to negative, that means our curve has to go through 0, which means W of t minus R of t has to equal 0 at some point on 0 to 8, which means W of t has to be equal to R of t at some point on 0 to 8. Okay, so if you want to pause right now, that's the first one. Take a break. And I'm going to go straight into the second question. All right, y'all, we're going to be talking about the 2015 question number 1. The rate at which rainwater flows into a drain pipe is modeled by the function R, where R of t is equal to 20 sine of t squared over 35 in cubic feet per hour. T is measured in hours. and the interval is 0 to 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate modeled by d of t is equal to negative 0.04 t cubed plus 0.4 t squared plus 0.96 t cubic feet per hour for 0 is less than or equal to t is less than or equal to 8. There are 30 cubic feet of water in the pipe at time t equals 0. At this point, you're probably wondering why calculus teachers are so concerned about rainwater flowing through drain pipes. But, things happen. Lots of rainwater. We go and stare at the rain all the time. All right, so for part A, how many cubic feet of rainwater? I feel like that should be how much. But anyways, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval 0 is less than or equal to t is less than or equal to 8? So we just want to know how much rainwater goes into the pipe. I'm not concerned about water draining out. I'm not concerned about the amount of water that is there to begin with. I just want to know how much water goes in. So I have an equation for the rate of water going in. So if I want to find the amount, I'm going to integrate backwards to find that total amount that goes in. So for part A, we want to find, go away. For part A, I want to find the integral from 0 to 8 of, I believe it's r of t, right? Yeah, r of t. And when you're writing for your exam, you can be that lazy. You don't have to write out r of t all the way. You can just abbreviate and say r of t. So the integral from 0 to 8 of r of t dt, 20 sine of t squared over 35. So math, option 9 for that function integral, 0 to 8. 8. And then it's 20, I believe. Yep. 20 sine alpha y equals, first option for that fraction, t squared over 35. Close parentheses. And then dx. Now, as always, it's a pragmatic moment to make sure you check on your calculator that you're in radians mode. I am. Everything for the calculator exam will be in radians mode. Hit enter. We get 76.570. It doesn't tell us to round to a whole number. Nope. So we are good. As always, I just like to check to make sure we're good. Yep, 76.570. All right. And then units, cubic feet, so feet cubed. Remember, we always want to talk about units when they include them in the problem. Never know when they're going to take off a point for no units. All right, B is the amount of water in the pipe increasing or decreasing at time t equals 3 hours. And give a reason for your answer. All right, so is the amount of water in the pipe increasing or decreasing at time t equals 3? So the amount of the water in the pipe is going to be dependent on two things. It's going to be dependent on R of t, rainwater flowing in, and it's going to be dependent on d of t, rainwater flowing out. I'm also talking about the exact amount, so I am going to include that 30 cubic feet of water in the pipe at time t equals 0. So for part B, this is going to be the first time of our mega equation for this one. So 30 plus the integral from 0 to t of r of t minus d of t dt. So that r of t minus d of t, that's rainwater going in minus rainwater that's draining. Then I want to know if this equation, that this amount of water is increasing or decreasing. So if I want to know about increasing or decreasing, what am I going to do? I'm going to go to the first derivative. So I need to derive this equation. So the derivative of this would be 30 is going to go away. Derivative of the integral is just the original function. So r of t minus d of t. Okay, so that's our first derivative. Now, I want to find if this derivative is positive or negative, because if it's positive, it's going to be increasing the amount of water. If it is negative, it's going to be decreasing. And I just want to find it specifically at t equals 3. I'm not trying to find intervals or anything yet. I'm just trying to find it at t equals 3. So R of 3 minus D of 3 equals. So I'm going to plug both these equations into my calculator. So 20 sine alpha y equals, I believe it's t squared. Yep. So 3 squared over 35 minus, and then it's negative 0.04 t cubed plus 0.4 and then 0.96 squared plus 0.96 is 3. It's that big old mess. So we get negative 0.314. Okay, so since R of 3 minus D of 3 is negative, that means we are going to be decreasing the amount of water. So R of 3 minus D of 3 is less than 0. Therefore, the amount of water in the pipe is decreasing at t equals 3. Okay, so once again, using our calculus house, talking about increasing, decreasing. One of the things you probably started to notice with these is, contrary to when we did our chapter 4 test, you're not really going to get questions where it's just calc house all the way through. They're just going to kind of stick it in parts. So you always kind of need to be ready to be able to bust it out. All right, part C. At what time t from 0 to 8 is the amount of water in the pipe at a minimum? Justify your answer. It doesn't specify absolute minimum, but I mean, they're basically asking the absolute minimum. Sometimes they're going to leave out absolute, but essentially, we're going to find any relative maxes or mins, only caring about the mins, obviously, and then we're also going to compare the endpoints. So for part C, we're talking about the amount of water in the pipe, so we're using that big equation for part C. So 30 plus the integral from 0 to t of r of t dt. It's not that big mess. Right? And then we want to find this. We're trying to find when the derivative is equal to 0, because I want to find any relative maxes or mins. So once again, we take the derivative, which is just that r of t minus d of t. Now I'm going to set that equal to 0. And I'm going to go search for any of those maxes or mins. Now, a lot of y'all have been asking how to do this in the calculator. So go to your y equals. We're going to put both of these equations in. So 20 sine of t squared over 35 minus, make sure I put everything in parentheses, so 0.04 x to the third plus 0.4 x squared plus 0.96x. And the other one I'm going to put in 0. So y1 I put the r of t minus d of t, y2 I'm putting in 0. We go to our graph. It's probably going to be a mess. Oh, it might not be too terrible. Oh, what did I mess up? All right, so I figured out what I did wrong. I forgot the negative in front of the 0.04. So calculator / trying to read and make a video at the same time error. But now that we add that negative, we go to our graph. Still kind of like not the greatest in the world, so we can adjust the window a bit. I don't really care about anything except 0 to 8, but I'm going to go just a little bit bigger to make sure that I can see everything. Y min and Y max is probably fine. All right, And I don't care about that one either, so I am just going to take out that last bit there. So I can just see really 0 to 8. There we go. Okay, so we can clearly see there's one right here at the beginning, which that's good to know. One of our endpoints is actually a relative max or relative min. And then we have one here in the middle. So second, calculate, option 5, intersect. And I'm going to arrow on over to that intersection point, hit enter 1, 2, 3 times, and it'll give me that intersection point, 3.27165. Okay, so now I'm going to find, if you've noticed on the scoring reports, they like to make a little table, which tables are kind of cool. So t-value of 0, 3.27165, and 8, and I'm going to find all of these values. Now, remember, I'm just plugging t in here for length of the video's sake. I'm just going to pull those values real quick. So 30, 27.964, and 8. Oh, sorry. At 8, 48.543. All right. And the question actually asked us, at what time is the amount of water in the pipe at a minimum? So out of these three, 27.964 is the least. So we'd say the water is at a minimum at t equals 3.271 as in hours. Doesn't really matter when you're just talking about it like this, but doesn't hurt to include it. 3.271 hours, because we could say the value is less than value at t equals 0 and t equals 8. You might notice that was probably not my greatest written out answer ever. But once again, once you've shown all this work that's here, you're really just summing up that, like, hey, I found my work up here. So it's less than those other numbers. Those other numbers, that's the work. So take it or leave it. All right. Part D, the pipe can hold 50 cubic feet of water before overflowing for T is greater than 8. Water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow, right? But do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Okay, so this question kind of reads a little bit confusing, but it's really not easy. It's not hard. It's like the easiest last little step you could ever think of. So all I want to show is, when is the amount of water in the pipe going to be greater than 50 cubic feet? At some point, the R of T is going to be greater than D of T for so long that there's going to be more water in the pipe. So all I need to show is, when is this equation, the equation we got in part C, this equation, when is that equation going to be greater than 50? Well, all I need to do is take that equation and set it equal to 50, so I can prove that. So for part D, I just want to say 30 plus the integral from 0, but instead of T, I'm going to say W, because that's what they tell us to use, time W when the pipe will begin to overflow, R of T minus D of T. And I'm going to set that equal to 50, as if I was going to solve this for that variable W. What would W actually equal? And then you're done. Nice and easy, because it just tells you to set up an equation, not to actually solve anything. So we are all good to go. All right. That concludes your walkthrough for last week's FRQ. Sorry it's so late, but stuff happens. Thank you all.